questions from the last time?
Sorry, camera is turned off.
Sorry, repeat that again.
Camera is turned off. We couldn't
it's on.
see the background. We couldn't see you.
You cannot see me, so how do I turn on the camera? It's on now, it's on. Video recording, how do I turn on the camera? You cannot see me.
Now it's okay.
Okay, maybe it takes a little while, I don't know. Okay. Good, so any questions? Okay, so as I was saying, I mean, maybe I will come back to this decomposition of tensor products.
So when we did the product of R3, so we make it RT, and then it's like the direct sums of the first one, R1 T plus I and I. So why we use I, the identity here?
Maybe I have to come and look at it. I don't know which one.
So it's like applying the algebra, R1 has R3, and then we got like this. Thank you.
Oh, yeah. I mean,
Why do we use the identity?
so, okay, yeah, I think that's important to understand. So in the tensor product, so let's suppose I have a tensor product of R1 times R2 times suppose I have something like this, tensor product. Now, so the first question you have to ask is how does the group, whichever group you're talking about, let's say SU2 group or whatever you're talking about, how does the group act? Right? So this is some G. This is a general statement, not just for SU2, for any group. And these are some representations of what this group, G. There's a G, this is a group, and the corresponding Lie algebra, which has been known by Lie algebra, which is, I think you're using V. And these are representations of V, which of course means that is a representation of G. Because as we have discussed, you can exponentiate the Lie algebra elements and their finite elements. So if the Lie algebra element is expressed in terms of some matrix, say some n-binomial matrix, so the representation is n-dimensional, then you have to exponentiate that matrix, and you will get the group elements, which will also be n-binomial matrix. So this is, okay, now suppose G belongs to G. Now the question is, how does this act on these representations, right? So it will be just given by G, I mean, well, R1G. So a general state will be, so this is so general state would be what? I mean, there will be some, so this can have many states. This can have many states. Let's say this is N1, dimension is N1, this is N2, and so on. So that means all possible states will be, you have N1 states here and N2 states there. Total number of states will be N1. So let's just focus on 2. So N1 times N2 is the dimension of this product relationship. Now what you do is when I apply G will act on this vector. This is some N1 dimensional vector. Okay. Times R2G will act on this N2 dimensional vector. So this is a notation. This is an N1 column vector, this is an N2 column vector. So it's simultaneous. You see, it's simultaneous acts on both elements. Now that is a level of a group. Now what happens if I look at the Lie algebra identity, let's say some x. So let me write G, which is close to identity. Okay. So the Lie algebra identity is taken by taking a G, which is close to identity, and we make an expansion, and let's say x plus order epsilon square. So let's just plug that in here. What does that mean? So we want to look at R1 G. Well, this is identity. Identity means the R1 of this is simply N1 by N1 identity matrix, right? So this will be identity N1 times N1. I mean, this is just to say that there is an N1 by N1 identity matrix. And then you will have plus epsilon R1 x. And the same thing for R2. So R2G will be identity N2 times N2 plus epsilon R2x. Plus everything is I'm ignoring all the epsilon square. So now just plug that in here. So what happens here? So this will go to, so that if I substitute this here, first of all, let's look at this term, and okay. There's a term which is accelerated to 0, right? Which means just this and that. Right? So that is identity. So identity N1 cross N1 acting on this vector times identity N2 times N2 acting on this N2 vector N1 vector. That's the first. That's epsilon to the 0. Now the interesting thing is what is the epsilon order which we are focusing on, right? Because that's the infinitesimal action. So this can come from two possibilities. I take identity from here and the epsilon term from there, or I take the identity from epsilon term from here and identity from there. Okay. So therefore, the one term will be identity N1 cross N1 acting on this times the R1 of x, R2 of x acting on this N2, plus the other one, so epsilon term is that, plus the R1 of x N1 times identity N2 cross N2. So that's why the identity comes. So as a result, you see, whereas here it was acting on both simultaneously for a finite group element. But when you look at the infinitesimal action, is this term. This term is a sum of two terms. One where the action is in the first vector, let's say here. This one is the first vector, it's acting on the first vector, and it doesn't do anything to the second vector, because identity doesn't do anything. Whereas, plus the other term where nothing happens to the first vector, and the infinitesimal transformation happens on the second vector. Right? So that's the... I mean, I will come back to this because anyway, for the SU2, we already saw a very simple way we can actually work out all the, if you take a tensor product of two representations, we worked out explicitly for spin half, no? Two spin halves. But that was one thing, I don't know if anyone tried. But if not, I mean, you got it. Okay, good. So in general, the thing is that if you take a J1 spin representation, times J2 spin representation. Sorry, again, I should emphasize that I'm denoting the representation by the spin. In the lecture notes, as well as in many of the books, you will see that what the notation is that you write it as the dimension of the representation. Okay. Times 2J2 plus 1. So in this case, you are saying a dimension. Instead of here, I'm writing spins. But anyway, I hope this will not create a confusion. So usually I'll be using this. Well, not really, because when I go to SU3, I will get back here, because there is not a simple thing like a spin there. Okay. In SU2, there is some quantity of spin. Spin labels the representation. In SU3 is more complicated. So in SU3, when I go to SU3, I will revert to the dimension, notational dimension. But for SU2, I'm just writing spins. Okay, so then this decomposes into several irreducible representations. So the highest thing is J1 plus J2. Now the direct sums of J1 plus J2 minus 1 all the way up to J1 minus J2 modulus. So if J1 is greater than J2, then it's just J1 minus J2, or if J2 is greater than J1, J2 minus J1. So this is what happens. There are several things you can check immediately. Because here you know the dimension is that. Okay? So does this agree? I mean, this dimension must be equal to also that. Right? Otherwise, if this is less than that, that means I'm missing something from here. No? Or if it is greater than that, that's impossible. You cannot have, right? So one check is to see that the dimensions of all of these things, which means dimension of this is 2 J1 plus J2 plus 1. Okay, dimension of that is 2 of J1 plus J2 minus 1 plus 1 and so on. All the way to the last one is 2 J1 minus J2 plus 1. So if you sum it up, do you get that? The dimension is, total dimension is simply 2J1 plus 1 times 2J2 plus 1 on the left hand side. So right hand side also better match the same. So this is one check. You could check that. Or of course, the other thing, I mean, this is just a check. But to really see that, you should actually look at all the T3 quantum numbers that you get. Just one comment about this. So what this means is that if I look at, suppose I have diagonalized all of these representations. I mean, I have diagonalized T3 in all these representations. So both R1, T3 meaning the SU2, the T3 that we were talking about, right? So both R2, T3 and R1, T3 are diagonalized. Which means we have chosen the eigenbasis for the T3 on both representations. Then you see that the way the eigenvalues just add up, right? So if I'm looking at eigenvalues, if I look at T3 action, this is an important point. So if I look at now T3, and suppose I have diagonalized, so we have diagonalized. T3. So both R1 T3 and R2 T3. So now suppose I look at, so this is all sorts of states, right? I mean, there are lots of states, which is the dimension of this and dimension of that. So in particular, let me look at a state which comes to the eigenvalue M1 for R1 T3. Okay. So I'm just denoting, so this is, I don't know what shall I call it. I mean, this is the state. This is the state. So what is this? Maybe I can write it like that. Huh? I can write it. Yeah, let me write it like that. J1 M1. I take the state from here, and J2 M2 from the second one. I take this particular state. Among many other states, I look at this state. And I ask the question, how T3 acts on this? So from what we are seeing is that this should be the sum of two terms. One where R1 of T3 acts here and nothing acts there. I mean, identity acts there. Or another one is when R2 T3 acts there. So when R1 T3 acts here, so let me just write that down. So J1 M1 times J2 M2. Because here is identity, so nothing has happened. Plus J1 M1 times R2 T3 at dimension. Now by definition, the eigenvalue of T3 for this state is M1. Okay. So this is simply M1 times the same state. And here, okay, nothing happens here, so this is the same. But when R2 T3 acts on there, its eigenvalue is exactly M2, right? So it's M2 times J2. So you see that the sum, total thing becomes M1 plus M2 times this state, which was the original state on which it was acting. So again, this state is an eigen state of T3, but with eigenvalue, which is the sum of the two eigenvalues. So this is very useful. This will be very, very useful for also SU3 when we discuss SU3. That always this in the product representations, direct product representations, the eigenvalues just add. On J? No, J is the total string, right? So in a given J1 is just labeled in the representation. So J1 is just labeled in this notation, is labeled in the representation. In this representation, what are the states? When I say J1, the states are M1 equal to J1, J1 minus 1, all the way up to minus J1. So these are all possible states. So the first label is just telling you, saying which representation you are talking about. Right? And the second one is actually the eigenvalue. These are the eigenvalues of T3. Right? So that's just the label. That is just remember that, yeah, we are looking at the spin J1 representation, and that's spin J2 representation. Okay. Yeah, I mean, to really prove this, one needs to show, because you see, if I say it is this, then if I look at a particular n eigenvalue, eigenvalue of T3 in the product representation, then, okay, here I can compute what is the degeneracy at a given n. No? This n can come from each of the representations, right? If the n is in the appropriate range. No? For example, if n is, modulus of n is less than or equal to J1 minus J2, then it will appear in each of the representation, right? Because, see, so what are the T3 eigenvalues from here? This will be going from J1 plus J2 all the way to minus J1 plus J2. Right? Similarly, here, all of this. And here, it will go from J1 minus J2 to minus J1 minus J2. So if I look at a particular eigenvalue, so this n can appear here. So if n is, for example, if n is, modulus of n is less than or equal to J1 minus J2, then this n will exist in all of these representations, right? It will appear here, then of course, therefore, this spin is only higher than that, so surely it will appear, no? So it will appear in everything. So the multiplicity will be how many such representations are there, okay? However, if n is, say, bigger than that, but less than, say, the previous one, less than or equal to the previous one, then only this much will appear. No? So therefore, you see that the multiplicity of a given n, for a given n, is not going to be fixed, it's going to change, depending on what the value of n is. So you should be, and exactly you can compute what the number is, what is the multiplicity. And you should get the same multiplicity from here, right? So that's the one. So here what is going to be? Here will be M1, which is going from plus J1 to minus J1, and here is M2. So we are asking how many possible ways I can get for this, so how many possible ways I can choose M1 and M2, such that M1 plus M2 equal to M. So how many ways? Let me just give you one example. Yesterday I did just spin half. Spin half was too easy. So let me just do one example. It will not be a proof of this statement, that is an example. But then you have to try to prove that. So let's just take an example where I don't take the same spins. I take two different product of two different spins. So for example, let's take say spin 2 times say spin 1. Okay, I don't want to take too large number, otherwise blackboard will fill it up. So spin 2. So spin 2, what are the eigenvalues? So here is the plus 2, I mean T3 eigenvalues. Plus 2, plus 1, 0, minus 1, minus 2. That is in this. In this you get, sorry, this is 1. Spin 1. So here I get plus 1, 0, minus 1. That's it. Right? 3 states here and 5 states here. Now, so when I do the tensor product, I can take the product of this state with that state, this state with that state, this state with that state, and so on, right? So total dimension of that is 15. 5 times 3. That's the dimension. So now let's take each of these states. So I couple these two and I put this times that. So what is the T3 eigenvalue of that? If I look at plus 2 times plus 1, it is plus 3. Right? Now let's look at the plus 2. Okay, maybe I should write like this. So T3, I want to look at all the possibilities. So maximum is plus 3. Right? And here I write the multiplices. The number of multiplices. Which is how many possible ways I can get plus 3? There is only one possible way. Plus 2 plus 1. Right? That's only one possible way. So that's just one. Now let's look at plus 2. Now there are two possibilities. I can take this state with that state, the product of this state with that state, or I can take the product of this state with that state. Okay? Nothing. I cannot do anything to get a total plus 2. So the multiplicity gives 2. Two different ways, two independent ways I can get. Plus 2. Then look at plus 1. Plus 1, I can get this times that, or this times that, or this times that. Right? There are three ways of getting it. That's three ways. Now, 0. Okay, you see this increases in 1. Question is about 0. 0, I cannot, if I start with plus 2, I can never get a 0, because here there is no minus 2. So the best I can do is to start with plus 1 and minus 1. Okay, that's one possibility. 0, 0, and plus 1, minus 1. Minus 1. This again cannot give you 0. Right? So there are only 3. Now, minus 1, this is going to be completely symmetric, the positive. Okay. That's easy to see. Because all these diagrams are symmetric. No? If for every plus, I can value there is a minus. So this is going to be completely symmetric. You can of course verify it, but from the symmetry you immediately see that multiplicity must be. It's important that here it does not increase. Why? Because J1 minus J2, J1 in this example, J1 minus J2, J1 is bigger than J2 first of all, and I'm calling this J1, and that's J3. And J1 minus J2 is actually equal to 1. So below 1, between plus 1 and minus 1, multiplicity is not changing. You will see that there is a general change, not just for this example. This is a general change. And now you can see how the representation is splitting. So first of all, I know the highest weight in the product representation, the highest P3 quantum number is plus 3. So there has to be a spin 3 representation. Right? That's the highest weight. So measure the highest weight. That's the n equal j. Right? So this j is n plus 3, then that's spin 3. This has how many states? Again, write down the multiplicity, so let me write down spin 3. The multiplicity of course will be 1, 1. Everything is 1, 1. So maybe this is everything is 1. Here I'm just drawing a horizontal line so that I see I'm writing in the right place. Okay, so now, so I know that this representation is spin 3 representation exists. But that cannot be the whole thing, because spin 3 accounts for multiplicity 1 each. for each of these three contributors. Whereas here, this is fine. This has been taken into account. Similarly, this has been taken into account. This has been taken into account. But for the remaining ones, I have left over. So what is left over? If I remove this space, leftover space, here is 0. Here there is 1 because 2 minus 1, 1. And here is 3 minus 1, 2. Again, 3 minus 1, 2. And 1 and 0. What is happening? 3 minus 1, 2, 2. 2. 3 minus 1, 2, 2. And 1, 0. Now look at this remaining ones. What is the highest HEP contributor? Is 1. It is for the plus 2. Plus 2, there is 1 state. So this must be a highest weight state. Nothing else. Once I remove these states, then from the remaining ones, this must be a highest state, highest weight state. Okay? So that means there is a spin 2. Spin 2 representations. But this will take care of 1 each from this. Right? I mean, this is 0 here, 0 here. So again, subtract that. So when you remove these states from here, then what is left over is 0, 0. Here you get 1, 1, 1, 0, 0. That's what's left over. After having taken into account this and this is still left over. And here the highest weight is T3 eigenvalue equal to plus 1. So there's a spin 1. And that's it. Because spin 1 takes care of all these 3 states. Right? So therefore we see that this reduces to, so spin 2 times spin 1 reduces to spin 3 plus spin 2 plus spin 1. That's it. And that's exactly the formula we were saying. This starts from J1 plus J2, which is 3, up to the modulus of the difference. So 2 minus 1, 1. So this. So the crucial thing to prove here is that once you reach J1 minus J2, modulus of J1 minus J2, after that the multiplicity doesn't change. Up till then, multiplicity increases by 1 unit. And that will prove this formula. There is of course, this is now tensor product of 2 representations. In principle, you can have tensor product of 3 representations, any number of representations. That can happen. I mean, again, just like so far we were looking at diagrams like this. You're asking some representation, R1 comes, R2 comes, and then what representations can appear here is the question. No? Similarly, you can ask what happens I have a higher point interaction, R1, R2, R3, and this whole thing is coming and going into something R4. What are the all possible R4s if I fix these 3? So then so you can talk about arbitrary tensor product, arbitrary number of tensor products. So there is a whole discussion in this chapter which is so-called the tensor analysis. I will come back to that maybe later, after discussing this. Because for ST2 we don't really need all that because it's very simple to do this calculation. We can very easily work out the representations, irreducible representations. But simply express simply express. So maybe then I will come back to it.
Professor, one question. Yeah. When you have more than 2 of these things, you obviously first sum the first 2, and then you, for each of the reducible representations, sum the other.
Yeah, exactly. So for example, now suppose on top of it I have a spin half. Suppose I want to multiply the spin half. Okay. As an example. Then you have already worked out this, right? You already worked out this spin 3 plus spin 2 plus spin 1. So you can take that. So we already have this thing. Now what I have to do is I have to take this and multiply this to spin half. Then as you were saying, so what will happen? You have spin 3 product spin half plus spin 2 product spin half plus spin 1 product spin half. So each one of them you can then do. And then, so you've got a big thing there. Yeah, so it starts to become very cumbersome. You know, the number of such factors increase. It starts to become very messy to do. So there is a procedure called Narain. It gives you a very nice kind of procedure to just, you can, some draws and diagrams and construct it. But let me, for the moment, forget about it. If there is time, I will see how it goes, whether I have time or not. Any questions from here? Yeah, I mean, okay, so this is one more point, that's actually one more point I should say, is that, I mean, so far we looked at the algebra, SU2 algebra, and we constructed the representations, all the irreducible images, but I mean, if you don't look at SO3, after all, SO3 and SU2 have the same algebra, so you would say also SO3 has all of the representations. But that's not the case. In fact, that is where at the level of algebra, they have the same representation. But algebra is not enough. You want to promote it to the full group eventually by exponentiation. Okay. So the question is whether once you go to the group, at the group level, can you have all these representations for SU2 and SO3? It turns out that for SO3, you don't have half integer space. Okay. You only have integer space. Okay. So how does one see this? And there's one way to see this is, you remember that we discussed that SU2 and SU3, I mean 2 points of SU2 are mapped to 1 point in SO3, right? There is a, so G and minus G of SU2 are mapped to the same element in SO3. So now let's look at this element here. So that's also I mentioned about the center. So if I look at SU2, you have these two elements, identity, of course, this is identity element, and also the minus 1, 0, 0, minus 1. Both of these elements are mapped to the identity element of SO3. This is the identity element. So which means both are mapped to 1, 1, 1, 0. 1, 1. This is now I'm talking about at the group level, not at the level of Lie algebra. So both of these elements were mapped, we discussed that I think, to maybe last week we discussed this. Both are mapped to this same point. Now, so essentially what we want to ask is that if I look at a given representation, some representation, and consider the action of this element and that element, okay? If they are not identity, both of them are not identity, then it cannot be part of an SO3, it cannot be a SO3 representation. Because from SO3 point of view, both of these points, both of these elements are identity. So if it has to be a representation of SO3, then both of these must act as identity on the SU2 representations that we have talked about. So let's just let's try to see how we can do that. Well, this I can write. I can write this as both of this. I can write it as e to the power of I theta. So let's consider this element, sigma 3 by 2. I theta sigma 3 by 2. That's easy to construct, e to the power of I sigma 3 by 2. Because sigma 3 after all is just 1 minus 1, 0, 0. And sigma 3 square is of course 1, 0, 0, 1. So I can immediately write down, this is nothing else but, I mean if you exponentiate it, it's clear it's going to be e to the I theta by 2. And e to the minus I theta by 2. It will be the diagonal matrix. So this exponential, using the fact that sigma 3 is simply the diagonal matrix, okay, is just going to give you e to the, so the top component is 1/2 because this one, I mean I theta by 2, and the bottom component will be e to the minus I theta by 2. You can, so this is what you get. So this element is nothing else but that. Okay. Now, so if you look at now theta equal to 0, so theta equal to 0, theta equal to 0 gives you just that. Huh? Theta equal to 0, so theta equal to 0 is the, let's call it identity, and this is the minus identity. So this is theta equal to 0, this guy just gives you identity. But theta equal to 2 pi, it gives you minus identity. Okay. And theta equal to 4 pi, again back to identity, plus identity. So theta, this is theta equal to 0, and that's theta equal to 2 pi. Now, from the SO3 point of view, theta, its periodicity is 2 pi. That was a statement that both of these guys have identity. So SO3 is a rotation. 2 pi rotation does nothing, no? Is the same as identity. So the question is now whether these two are the same. Okay, so let us look at the fundamental representation, for example. In the fundamental representation, which is R of sigma 3 by 2, is simply sigma 3 by 2. I mean, this is the defining representation itself is, so this R fundamental, sigma 3 by 2 is just that. So for that, we have already computed what is e to the I theta. I mean, we already computed this. So e to the power of R theta R sigma 3 by 2. This is identity for theta equal to 0 and minus identity for theta equal to 2 pi. So you see that on spin half representation, these two elements are not acting as identity. This one acts as 1, this one acts as minus 1. So it cannot be a representation of SO3. Okay? So in fact, the conclusion from this is that, on the other hand, spin 1 representation, you already know that is the SO3. It gives you the SO3 matrices, the spin 1 representation. This we have done again before. So the conclusion is that all the integer spins, integer spin representations are also representations of SO3. But the spin half integer, I mean, n plus j plus half integer spins. In other words, it's some odd number divided by 2. Odd number divided by 2 spin. Buckets to 2 are not SO3 representations. So this is just to indicate that the global structure, I mean, the algebra is blind to the global structure. The algebra is only the neighborhood of the identity. It doesn't know, it doesn't care about far away places. But the global structure does impose some conditions on the representations. What else I have to say? Yeah, I think I can. Can someone say what are the, since we discussed about SU2, what about U1? This is the easiest thing, right? U1. The dimensions of the used representation of the water for the U1. I mean, the answer is the dimension of the used representation is always 1. All the used representations are dimension 1. For a abelian group, that's what happens. All the representations are just one dimensional. And all you say, you can just define the eigenvalues. So, for example, if you take the U1 is parameterized by e to the I theta. So, e to the power of I theta times the generator T. Where T is just one generator. Okay. For the U1. And TP of course some loops and there's something else. So any representation is simply labeled by giving the eigenvalue. So they are all one-dimensional representation. So let's say some state the eigenvalue could be something, whatever it is, say x, x times this number. So this is the generator, that's the number. So this is the eigenvalue. And that's it. There's nothing else to do, because there are no, unlike in SU2, there was raising and lowering operators which could move you up and down, right? Here there's nothing else. This is it. Right? You want this is all this. So this is a one-dimensional representation. Okay. For any x. So the representation is labeled by this eigenvalue. However, not any x. You see, at the moment, from this discussion, I just say that it's some real number. Since T is Hermitian, this is some real number. No? But that's not enough, because I need to again see the global structure. Globally, if it's defined or not. This has a U1 periodicity. Theta equal to theta plus pi. It was periodic. It was the same element, the U1. Right? So we want to show that if I consider this action, it will be either T on state, which according to this formula, it should be equal to either x. Then this will be periodic under this will satisfy the periodic condition only if, so periodic condition implies that x is an integer. Because if theta goes up plus 2 pi, the extra phase is going to get to the power of 2 pi x. Right? But that you want periodicity, so equal to 2 pi x must be an integer. Which means x must be an integer. So this is the conclusion for the one. This again plays a very important role in particle physics. In fact, electromagnetism is basically one here. The semi-similar electromagnetism is one. And this eigenvalue that we are talking about is nothing but the charge, electric charge. So that this x plays a role of electric charge. And you know the electric charge quantized in some basic unit. That contribution is first. On the contrary, this was because we are talking about the U1. What about the R, the translation? R, remember we talked about one group R, which was just a translation along the real line. Translation by opinion. So you have a real line, and the elements are simply any real numbers. So this is all where A belongs to where A is the real number. And its meaning is simply translation along one axis. So if you have an x-axis, you have a specific x goes to the axis. So you are shifting. If you look at that generator, there is a condition like this. Right? So the eigenvalue of this generator, the corresponding generator, eigenvalue are all real numbers. All real numbers. And you know physically what this eigenvalue means? Anybody? It's the momentum. It is the momentum along that direction. If you are talking about the x-axis, there's a translation between the x-axis, then there is this eigenvalue. But momentum is not one point. Momentum can be any number, right? Okay. Now let's go to SU3. The strategy that we are using is basically to use as much as possible our knowledge of SU2 to understand SU3. This is the real strategy. Yeah. Let's just do that. Let's discuss quickly. So what is S3 by definition? Or the moment what is SUN? So SUN are unitary bases. So n by n. Unitary bases. SUN is a set has unitary bases. With determinant equal to 1. That's a definition. So that's my unitary basis is equal to 1. Now, so you have what condition? If U belongs to SUN, then from these conditions, we are saying that U dagger is one identity and digit U. So how many we can compute how many conditions there are? Well, first of all, if you look at U dagger itself is definition, right? Because if I take U dagger and take the dagger of that, then it's going to be when I take the dagger, I can change the order. So it will be U dagger and U dagger, right? But U dagger is U, so it's U dagger. So it's definition. So left-hand side is definition. So it's n by n definition matrix. So how many independent conditions are there? You see, definition matrix means what? So you have definition matrix means these are real, the diagonals are real, and all diagonal terms, if this is Z, then this should be R, right? So whatever the numbers are complex numbers here, but on the transpose of it, on the other side, it will be the complex conjugate of that. That is what Hermitian means, right? Because when you take the dagger, you have to take the transpose and complex conjugation. So when you take the transpose, the diagonal doesn't change. Then that is a condition that complex conjugate of the diagonal must be equal to the original diagonal. So therefore, it must be real, right? And this condition comes from the fact that when you take the transpose and the complex conjugate, it gives you the same as the original matrix. No? So that is what. So therefore, I mean, so the condition, what this equation is saying is that all these diagonals must be all 1, right? And off-diagonal guys are all 0. That's what this condition is saying. So how many conditions are there? You have n real conditions, right? From the diagonal, and real conditions from the diagonal, from considering the diagonals. And for every off-diagonal term, there are 2 conditions because it's a complex number. You are setting a complex number to 0, which means the real part is 0 and imaginary part is 0, right? So 2 conditions. But how many are there? There are the off-diagonal terms. Upper off-diagonal term is half n times n minus 1, right? Half n times n minus 1 complex equations. So that means 2 times 2 real equations. Right? So, I mean, these are the number of elements in this. If you just look at the upper triangular part, half n times n minus 1. And then these are complex equations, so which is equivalent, each complex equation is equivalent to 2 real equations. Okay. So the total number of real equations coming from the off diagonal is that. But once I have satisfied this, then these are automatically satisfied. Because if I set this z equal to 0, then z bar is also 0. Right? So this is odd. The total number of equations is this plus that, which is the same as n plus 2 and half cancels, so you get here n squared minus n when I open this bracket, and n cancels. So you get n squared conditions. Right? But the original U matrix itself, this U matrix itself has n squared complex. So you have 2n squared real. So U contains n squared complex, or equivalently, which is the same as 2n squared real variables. So you have n square conditions and 2n square real variables which exist, n square real conditions and 2n square. So the total, so you can see that by solving this equation, you will fix n square of those parameters, of those variables, right? But n square will still be free, right? I mean, this minus that will be free variables. Okay? So the number of free variables is n square. That is, still I cannot impose this condition. Just from this condition, just coming from the new parameter. This implies there are n square real variables left over. Still left over, which you can calculate. So if you don't have that condition, then this group would be UN. So UN has dimension n square real dimension. But we have also this condition. You see, okay, now one might imagine that, well, U is a complex matrix, so determinant of U should be complex, right? So actually this equation should be two equations, two real equations, right? I mean, left-hand side, in general, you might imagine, in general it will be, of course, complex. Determinant of U will be complex, if U is a complex matrix, right? And then this equation, so this will have a real part and imaginary part. And you set this equal to 1, that means the real part is 1, imaginary part is 0. So you get two real equations, right? Generically. However, we have already assumed that our matrix U is satisfying this equation. Okay? If this equation is satisfied, then take the determinant of both sides of this equation. So this gives you that U dagger equal to determinant of 1, which is 1. But this is the same as determinant of U times determinant of U dagger. But determinant of U dagger, I mean, transpose is the same. Transpose of a matrix, when you take a transpose, determinant doesn't change. So this is the same as U bar, right? The dagger is bar on transpose, so transpose doesn't do anything. So this is the same as determinant of U bar. So left-hand side is determinant of U mod square. So it's a real object. Right? I mean, left-hand side. So there's only actually one condition. Right? Because if you have already made sure that the magnitude of this is 1, because that's what this condition is telling you, that the determinant of U is 1. Determinant of U modulus is 1. I'm sorry. So this equation is already saying that, so this means determinant of U modulus is 1. Modulus of determinant is 1. So therefore, the determinant of U can only be a face. It will be ICTP or something else. So that is only freedom. Once you impose the unitary condition, then the determinant has to be of this form. A face, pure face. So this equation is saying that this pure face is just 1. But that's a condition on theta. Just one variable theta. So it just says theta equals 0, or 2 pi, theta equals 0. So this condition is fixing only one parameter, not two parameters, as the ideal one. Yeah, if this condition was not there, then indeed this would fix two parameters. But since I already imposed it, then we are left with only one parameter. So that's fixed. So therefore, since the dimension of this was x squared, this was the dimension of UN. And by imposing this condition, we are fixing one more n square real. We are fixing one more parameter. That means the dimension of SUN is 1 less than that. One real dimension less than that. So dimension of SUN is n squared minus 1 real. This I think we already, I don't know whether when we discussed this we did it in general like this, I don't remember, but I think we did it for SON. I think SON we did general. No? For SON, the dimension that we found was half and minus 1. For SON. For SUN, the dimension is square. So So what does that mean? Now let's go back to the Lie algebra. This was at the level of group element. So let's again look at the elements which are close quantity. So let's write U. So now we look at the infinitesimal derivatives. So U, we write it as 1 identity, so this is n by n identity, plus, say, epsilon. Let me also put here I times t. I mean, this I, if you don't put I, then okay, let me not put I for the moment. So just epsilon times t. And so then let's see what condition this imposes. So this condition imposes that, so if I take the U dagger, so U dagger is nothing else but again identity plus epsilon t dagger. Epsilon is a real parameter. I mean, it's the infinitesimal epsilon. So then if I plug that in here, in that equation, then you see you will get the first term, I mean, this times that is the identity. So U dagger. You gather the identity. Plus all the epsilon term will come when this times that plus that. Right? So you will get here epsilon t dagger plus I order. And that's supposed to be equal to identity. So therefore we conclude that t must be anti-dimension. T dagger is equal to minus c. That is why so let me go back and put here I, so that I only never do the Hermitian. Just like what we did for SU2. We did the same thing for SU2. We put an I there. I times sigma. No? So if I put that, then here this will be minus, because when I take the dagger, I take the complex conjugate, this becomes minus. So this is going to be minus that, and in that case, I minus that, and we'll do this. So T is I mean, this is not important, this doesn't matter, but physicists like to work with the Hermitian cases. So just for mechanism. So this is Hermitian. But now, Hermitian matrix, how many variables are there? N times n square, to begin with n square. But this condition will basically just give you n square area, right? This is a thing we already used in checking things, right? We said that U dagger is a Hermitian matrix. And so therefore it involves n square variables, right? N square variables. So that was n square. It's just the same thing, because the T-diagonal thing is diagonals of course real, and the off-diagonal terms are complex conjugate when you do the transpose. So off-diagonal terms are complex, but then the transpose of it is just a complex conjugate. So that gives you total n square. The same thing. And finally, we have still imposed this condition. I mean, so far we only imposed the U dagger condition, which agrees because also we found for the UN dimension as n square. And here we are seeing the same thing. N square real values. That's a dimension. But when you impose this condition, then you remember we discussed that is the same as tracelessness condition at the level of the. So did you equal to one condition implies that when I express this infinitesimal change, that this is like a trace of T. That's why the coordinates is about traces. I mean, we did that as well. So trace of T equal to 0. So that removes one variable. Okay. So this was exactly the conditions we had done, but I don't remember whether we discussed SU2 in general terms, I think, or we just worked out 2 by 2 matrices. That's why I did this general. Okay. So now let's specialize it. So the 3 by 3 matrices. So all we want to do is to write down all the so the Lie algebra, so the SU3 Lie algebra, so which I think in this notes we are using small s, SU3 Lie algebra, is a set of 3 cross 3 Hermitian traceless matrices. This is, the dimension of this is, we saw, is 3 squared minus 1, which is 8 dimension. So just like for SU2, dimension was 3, and we chose some convenient basis, which were the polynomials. We chose the polynomial as a basis. 3, we need to choose a basis. We just write down some basis, and I will just, you have the, I'll write down the basis here. These are the so-called Gell-Mann matrices. Gell-Mann was I think the first physicist who used SU3 in the context of particle physics. Gell-Mann matrices. So it was, so let me just write down once, lambda 1 equal to 0, 1, 1, 0, 0, 0. Lambda 2 equal to 0, lambda 3. Sorry?
I think someone.
Yes, sorry. I'm sorry, there's a lot of disturbance. I cannot hear you very well. There's a lot of disturbance.
So you can't hear yourself here.
You cannot hear me? But also his voice, there's a lot of disturbance. Hello? Can you hear me now?
He said he can't I can't do so I think his internet connection is weak for the moment.
Okay.
Because I can't hear him also.
Yeah, I mean, I can hear your voice very well now. But
Yeah. It's hard, not me. I can hear you very well. I think our connection is not good.
Okay. This is a problem. But can you follow the video recordings later? Or even there is some problem. There is, sound quality is not good there. But you can see the blackboard well?
Yes,
Blackboard you can see. Okay. Now, yeah, this is the problem. Yeah, so then there is this. So 1, 0, minus 1, 0, 0, 0, 0. Okay, then there are a few others, but already let's look at here. You see, what is happening here? This was, if you just focus on this 2 by 2 part of these 3 matrices, this is simply sigma 1, sigma 2, and sigma 3. right? So already we see that this forms an SU2 subalgebra, right? Because nothing happens, rest of the things are 0, so that will not enter in the, when you take the product or the matrices, this will just disappear. Okay, now with the remaining ones, so let's look at lambda 3, lambda 4. So lambda 4 is 0, 0, 1, 0, 0, 0, 1, 0, 0. Lambda 5 is 0, 0, minus 5, 0, 0. Okay, lambda 6 is 0, 0, 0, 1. Okay, this is just a basis of the this Hermitian traceless matrices. Lambda 6 is here, and let's write down lambda 7, which is 0, 0, 0. And finally, lambda 8 is 1 over 3. Now this looks very ideal, 1 over 3. But there is a reason for it. Okay. So these are the 8 matrices. Of course, you can choose in different ways. But the important thing is that this forms one SU2 subalgebra. And actually, you see, you can also consider the following. If you look at it, you can derive this in a different way. You can write this as some combination of lambda 3 and so, for example, let's see. If I take lambda 3, lambda 8, lambda 8 minus. So let me multiply by root 3. Root 3 lambda 8, so the root 3 disappears. And then I want to use the lambda 3. So minus lambda. Consider this combination. So what's going to happen there? And divide by 2. It's 14 divided by 2. So root 3 times 2, so it's just this part. And I want to subtract from here this. So this 1 cancels. Okay. And 1 minus 1 is 2. So this first part is 0. Of that, that's 0 both sides. So don't worry about that. So only to worry about this diagonal part. So here we say this is 2, but I'm dividing by 2, so it's 1. Right? And then here, nothing happens because the lambda 3 has no component like this. So this still stays minus 2. Minus 2 divided by 2, minus 2. Okay? So a certain combination of this and that. So if you take this guy and lambda 5, lambda 6, and this one. So this guy, together with lambda 5 and lambda 6, this will form another SU2 subalgebra. Because it's just now looking at, you see, this is like the first, this and this is 0. And here you have a sigma 1, lambda 6, no, lambda 6, lambda 7, sorry. Lambda 6 and lambda 7. Lambda 7 here is sigma 2, here is sigma 1, and here is sigma 3. Okay? So this will form another SU2 subalgebra. And finally, you can do also something else with these guys. So with these guys, what we want. So if I think of remove the second row and second column, right? So then the polynomial sigma 1. That's sigma 2. Now if you want to get something which is like sigma 3, you should have 1 minus 1. Right? But then again I can choose some other combination. So now I want to get rid of this guy. So let's do root 3 lambda 8 plus lambda 3 by 2. So if I now do plus, you see this guy will cancel, the middle one will cancel, right? And you are left with 1 and minus 1. I mean, there's a factor of 2. So this is nothing else but 1, 0, 0, 0, 0, 0, 0, 0, minus 1. Okay. So there are these 3 SU2 subalgebras inside. Already we see directly. Okay. It's a matter of choice of it. But these SU2 are not independent. They are not, they're kind of, if you take, so if I take commutation relation between lambda 1, lambda 2, lambda 3, just these, then okay, this is an SU2 subalgebra, right? Similarly, if you take commutation relations between this, that's again another SU2 subalgebra. But it is not that these two SU2 subalgebras do not talk to each other. They do, they talk to each other. Okay? Meaning the commutators of this SU2 subalgebra with that SU2 subalgebra is not 0. Okay? So there are SU2 subalgebras sitting inside SU3, but in a very complicated way. Okay? They are not like communicating with each other. No. You can,
this is by choice.
Huh?
This is by choice. Doesn't mean you voting this state is posed by choice.
Well, I mean, he was just choosing some convenient basis. No, you can choose any basis, but of course, any other basis can be expressed in terms of this basis. Right? Because you're looking at all the revision, 3 by 3 revision matrices. So, if you dispute, with the trace equal to 0, right? So that is all you can do. No, this is never unique. Yeah. You can always choose a linear combination of the old basis and a new basis. Yeah.
But it will always be a linear combination. It will always be a linear combination.
Yeah. Because there is any 3 by 3 matrix, I can write it like this. That's it. One can see that, right? If I write the most general Hermitian basis matrix. So here it will be all real numbers. Let's say x, x1, x2, but then this should be minus x1 plus x2, right? Because the trace has to be 0. X's are real, xi are real. Okay. Now here I have complex, say z1, z2, z3. Then here it has to be z1 bar, z2 bar, z3 bar. That's the most general thing. Now let's rewrite this. Z1 is, I already used x1. Let me call it something lambda, let's say. No, lambda I'm using there. So xy, u1, let's say. u1, u2, u3. So u1, and here is u1 plus u2. u1. And let's call this x1 plus i1. This one is x2 plus i1. x3 plus i1. Now they are real, and here the complex conjugate of that, so it's x1 minus i1, this is x2 minus i1, and that's x3 minus i1. Right? Now you can see, so let's try to write, this is the most general matrix, right? Which is Hermitian and traceless. So you see this x1 times lambda 1, so this I can write as x1 times lambda 1. Plus I. Okay. Minus I, y1. No. So this is already plus I. So minus y1 times lambda 2. Okay. That's that. Similarly, x2. X2 times lambda plus x2 times lambda 4. And minus y2 lambda 5, right? And look at x3 plus x3 lambda 6, and minus y3 lambda 7. Okay, that is that. And then now the only thing left is the diagonal. So you can find some combinations of this. So you want to write this U1, U2, and this guy as some combination. So let's call it W1 lambda 3 plus W2 lambda 8. You can easily solve for this. Just W1 and W2, you can solve in terms of this U1 and U2 by using. What this would say? This would say let me put here root 3 because root 3 is a mess. Root 3 lambda 8. So W1, so that this means that if you look at this matrix, what is this diagonal matrix? So you have W1 lambda 3. So W1, and here lambda 8 was that. So root 3 lambda 8 is just that matrix. So plus W2. Here you get minus W1 and plus W2. And here you simply get minus 2. By just using explicit forms of lambda 3 and lambda 8, you see that this object is nothing else but that. This is everything else. And now you can, so we are saying W1 plus W2 is U1 and minus W1 plus W2 equal to U2. And indeed, you see, if you add these two, U1 plus U2, so the W1 cancels, you get 2 W2. There's a minus here, and that's minus 2 W2. I mean, because that's everything was built in, because it's traces, so it had to be traces. But this you can easily solve, right? So W1, yeah, W2 is U1 plus U2 by 2. Yeah, you can solve this easily. So that means any matrix can, any Hermitian traceless matrix I can expand. I can expand this basis. But it doesn't have to be this basis, you can choose some other basis.
And it's purely coincidental that it just happens to contain a
Sorry,
it's purely coincidental that it happens to contain some algebras as you do?
Well, not really, no, because I mean, if you say I have a 3 by 3 traceless Hermitian matrix. Okay. Now, if I take all the 1 row and 1 column 0, like this, no? Then the remaining thing is a 2 by 2 matrix, which has to be Hermitian traceless. So it had to be part of SU2 anyway, right? It has to be SU2 sub-algebra. So it's not surprising at all. Huh? Or you could have, so this was that's what you this algebra. Or if you choose something else, second column and second row 0. No? Then this, so this will again be an SU2 sub-algebra because this has to be Hermitian traces. So it was guaranteed. It was guaranteed.
So how many SU2 sub-algebras?
There are three here you see. Yeah, you could choose any row and column to be 0, right? Here was the second row column, before I did the third row column, or no, first column, that will be this that will be this one. I think this algebra, right? No. That one is, yeah, that one is this algebra. I mean, this guy. This together with lambda 6 and lambda 7. So it was guaranteed. It had to be.
The numbers are algebras, can we see like the trend if we go to higher, like more, like 4 by 4, 5 by 5?
Yeah. In fact, this will help us a lot. I mean, the fact that since we know everything what it's everything meaning that we know all the elements of the No. So this is not just this fact will help us a lot in understanding SU2.
Is there a kind of like number like the extreme in SU3 will the numbers that we would refer to like high dimensional?
Yeah. So I mean, this kind of there may be other ways of also building SU2 but this way of implementing SU2 algebra has to, there is a way you can count, which I think I have to wait a little bit. I mean, when we discuss, this will be discussed later. Not in the SU2 context, but after that we will generalize something. When we generalize, we will see that there is some concept, root. I think I already mentioned you root. No? I mean, it was not important, but we use this term root because there is sigma 3. We looked at the sigma 3. We took the sigma 3 because of the one out of this 3 for SU2. Let's go back to SU2. So you have sigma 1, sigma 2, sigma 3. Choose sigma 3 as you can only choose one maximum between sub-algebra will do always one dimension. So let's choose sigma, which is already diagonal. Then we found that you can get the raising and lowering operators, which were the sigma 1, sigma plus and sigma minus. No? And they had an important property that they were kind of eigen, let me call it eigen functions of adjoint representation of sigma. Right? Adjoint of sigma 3 is commutator of sigma 3. So sigma 3 with sigma plus minus, the commutator, gave you back again some number times sigma plus minus. So plus minus sigma plus minus. So those plus minus are as eigenvalues, which I didn't define it properly, I will define it more rigorously when I discuss more general, right? More general discussion. Those are called roots. So the statement that for every non-zero root, there is an exclusive sample. So it depends on how many roots there are. So, yeah, just to make it you can easily relate it to the SU and N of SU. But we will discuss some detail. Hopefully we'll start from next week. No. Already yes. I'm going very slow actually. So, okay. Yeah.
Here in general limits, the off-diagonal elements are complex numbers.
Yes.
And when we look at lambda 1, lambda 2, lambda 3, and lambda 8 basis, I don't see any I here.
No, you don't see. Sorry, I didn't write it. Can you see this is I actually? This looks like 1, but this is I.
Okay.
Sorry, these are all I's. I should write more clearly. Minus I. Here, and three of them are. Okay, so this we will now very soon we will start using this. Actually, yeah, this root 3 looks quite ugly here, but there is a reason for that, because this satisfies, lambda satisfies a nice property. So there is a nice property here that this basis is chosen in a careful way, by Narain, because he wanted this to satisfy. Lambda A, lambda B, trace of lambda A, lambda B was 2 times delta A. So somehow you are taking the same. That is the reason for this root 3. Because if you take lambda A square, you'll get here 1 plus 1 plus 4, which makes it 6. So that is why there is a root 3 here. So the square of root 3 is 3, 6 by 3 is 2. So it's for this, to get this kind of a relation, German used this root 3 is 2. And the rest of it is clear, because the rest of the directly part of the, it's a 2 by 2 part was basically SU2, as polymatrices. Right? So for that, you can easily verify that this is the case. Polymatrix, yes, trace of sigma 1, sigma 2 is 0, right? Sigma A, sigma B is, trace of sigma A, sigma B is 2 times delta AB. So the rest of it will automatically satisfy. It's just this one which was a little problematic, that is why there's a root 3. In fact, this is, for us, more convenient basis will be not lambda 8, but choose one of these guys, maybe this one. Okay, for us, when we discuss in more detail later. For us, more convenient basis is this, but lambda 8 is replaced by that. Now, there's some things you can try to do. This is already, there's no point in doing it in the blackboard here. To try to prove this statement, lambda A, so now look at the commutators of this, because after all, we need to know what are the commutators. So lambda A over 2, again, just like sigma over 2, we always found it more convenient to use sigma by 2. No? So I'll just take this lambda by 2, lambda B by 2. commutator is some I times FABC is not epsilon ABC anymore, huh? Lambda C by 2. I mean, it cannot be epsilon ABC because epsilon is a third rank tensor, totally antisymmetric tensor. But for that, A, B, and C can only go from 1 to 3, right? But here A, B, C go from 1 to 8. So it's not epsilon ABC, it's some tensor, third rank tensor, where A, B, C are all going from 1 to 8. Right? Again, repeated indices are summed over. Where explicitly can you see that? I mean, just below 8 point, in page 49. Page 49. If you this equation is given below equation 8.21. So below equation 8.21. 8.2.1. So there is this commutation relation is given, where just below that, all these are actually, so what are these numbers? F123 is 1, and so on. You could please try to check that, just to be sure that you get it right. This tends to be totally antisymmetric. But it's not epsilon, because epsilon, for that it should be as 1, 2, 3, etc. It cannot be 1, 2, 8. But this is totally antisymmetric. And so that this is again another equation which is given, that you can show that 4I FABC is equal to trace lambda A, lambda B with lambda C. Trace. Because if you can show this, so you should be able to show it directly from here. This condition. You basically, okay, let's just try to do that. We said that this German matrix satisfy this condition. Trace lambda A, lambda B equal to 2. This is satisfied. This you can check it easily. And we already checked for lambda A square. That was equal for root 3. But then, so you can start from this equation and multiply both sides by lambda D, let's say. So to prove this condition. If I erase this is going to be on the blackboard, unfortunately. So let's start from this equation. So at this point, okay, this algebra has to close, right? Because this is a complete basis of Hermitian matrices. And Hermitian matrices, if I give the commutator of two Hermitian matrices, right hand side will be anti-Hermitian matrix. No? So that there's an I there. If I take out the I, then this will be a Hermitian matrix. So therefore, clearly I should be able to expand again. And it should be traceless also, right? The algebra closes basically, that's what I'm saying. The SUP algebra closes. So therefore, the commutator of any of the two elements, lambda A and lambda B, is going to be again I times some combination of lambda C, because lambda C, this lambda is provided basis. So whatever Hermitian object will be here, I can always expand it in terms of this, right? And here, basically what one has done is that it will be some coefficient, say C, some real coefficient, but the coefficient will depend on what A and B are choosing. So therefore I put also A and B to remember that which A and B. Because if I choose different A and B, this coefficient will be also different, right? So this is a matter of differentiation. Okay, we put also 2. So that is the relation. Now, if I start from this equation, let's multiply both sides by lambda d. So this is a matrix equation, right? So multiply on the right both sides lambda d. For arbitrary d, could be anyone, any d can be anyone from 1 to 8, and take the trace of this both sides. Now use this equation, trace lambda A, lambda B. This is how this is expressed here. So this gives you 2 delta CD. So this is the same as I times this 2, 1 over 2 times 2 delta CD. Of course, these are the numbers, so FABC. So this immediately proves that I times FABD, because when I sum over C, I will get, there's the summation over C. I sum over C, then I will just, this C is replaced by D because of delta CD. And that's this here. So this was the equation. So you see, I mean, there is just a factor of, so this tells me that 1/4 that trace of the commutator of lambda A, lambda B times lambda B is equal to that, which was the equation. So therefore, this implies then that this is totally antisymmetric, right? Why? Because you see, this has a cyclic property. And what is this object? This is nothing else but lambda A, lambda B minus lambda B, lambda A, lambda B. Trace, right? Now I can do a cyclic rotation. No? So, I mean, it's clear that this is antisymmetric in AD. That is clear, right? You can show that it's also antisymmetric in AD, etc., etc. So what I can do is I can move this lambda D here. Okay. So this is lambda D, lambda A, lambda B, and here move the lambda B there cyclically. No. In the trace, you can always move. There are 2 different terms, right? Trace of this minus the trace of that. So here I move here. Here I move there. So this becomes minus lambda A, lambda D, lambda B. But that's the same as the commutator of lambda D, lambda A with lambda B. So this tells me that that's the same as F. So ABC, ABD, DDAB. So there is a cyclic. So in order to go, so this was FABD. Again, there's an I there. And then that so this is IFDAB, but that's the same as that. Why? Because I moved the D 2 times. Right? So I don't pick up a sign. You should be able to prove that if I just exchange but on the other hand, this also shows that it is antisymmetric in D and A. Because this I know is antisymmetric in D and A. Right? So this is antisymmetric in, as it stands, as this equation stands, this is antisymmetric in A and B. No? But by manipulating here, we say that this is also equal to FDAD, but that is antisymmetric in DA. So therefore, it's also antisymmetric in DA. Right? And you can similarly prove by doing something else, maybe, for example, keep this as it is, but here, move this lambda B there. But keep this as it is, don't move anything. Then lambda A sits on the left hand side, and what you get is a commutator to DD. Right? Lambda B minus lambda D, lambda D. This is the commutator for lambda D. So it's antisymmetric in DD also. So you see, any pair you exchange is antisymmetric. So there's a minus sign. So this is totally antisymmetric. So that's actually that's important fact. You would not have obtained this totally antisymmetric if you had not chosen a normalization like this. Okay. This is why Gell chose this Not that this guy, I mean, this year done 1 over 3 was for that reason, to make sure that this is satisfied. Because this implies that if we see a total against. So it's easier to deal. Otherwise, you don't see the relationship with this FAC or BA, or this is also a relationship, but this one simplified. But it's not necessary. It will just not, FAC not have this property. If this was not true, the property total accessibility. It will not be there, but doesn't matter. It's, I mean, it's easy. It just makes it easier to visualize. Actually, this part is exercise. This was 8.2 exercise. Now, yeah, I think it's not out there. Next part of the joint action. Because if I start now, this will take some time. Any questions?
Can we think of this as a matrix? Trace lambda A times lambda B.
This is a matrix trace, lambda A. Yeah. I mean, yeah. So this is a 3 by 3 matrix. 3 by 3 matrix.
No, not matrix, metric.
Ah, good. Yeah. Actually, yeah. See, yeah. You're jumping ahead. Yeah, true. You're right. Actually, this will be a very important. When we go to the general discussion, not this actually specific example, but when we generalize to arbitrary reactors, there is a particular metric. This is a metric is the issue because, so what is, I mean, so the algebra is a vector space, right? But so far, we have not included a notion of what's the distance, what's the length of the vector. So that's when one says put a metric, that's what it means, right? To define a concept of distance in the vector space. So now, of course, you could have chosen any kind of metric, but there are certain metrics which you prefer, which is natural, in the sense that it should be it should have some invariance to it. The symmetry, this group that we are talking about itself is symmetry. So you want to make sure that this metric that you introduce has some suitable symmetry. And that metric goes under the name of Cartesian. So we will discuss Cartesian. That plays a very important role in the whole classification of the Lie universe. Yeah, we will discuss next week. Yeah, this plays an important role. So by choosing this, we are saying that the metric is very standard Euclidean metric. No? So, yeah, so it's a convenience. Okay, so if no questions, you meet tomorrow. I'm sorry, I think some of the audio system and so on is not working very well. Huh?
Yeah, Professor, I actually need some part of this lecture. I just wanted to know if we are going to skip the Young part for now.
If we are going to?
If we are going to skip the Young part.
Young part, so let me first finish SU3. And then I will see how much time I have left. Huh? Because there is the general discussion we have to carry out. I think 2 weeks will be time actually already for that. The general discussion, generally algebra classification and so on. It will take, but I will see. Maybe I will spend, if not the whole lecture, maybe half a lecture on Young tableau. Maybe. But after I finish SU3. I mean, after I discuss when I may come to the representation of the SU3, maybe then I will come back to the young tableau. Yeah. Okay. So, if there are no questions, then we see you tomorrow.